I have started the recording, and so this week we are going to discuss about MOSFETs, metal oxide semiconductor-based field effect transistors. And your homework 2 and homework 3 grades are already posted on Canvas. Your exam 1 grades will be posted by tomorrow. Now, this week we are going to talk about MOSFETs, and when we are done with MOSFETs, we are going to have two more homeworks. One of them would be on the DC analysis of MOSFETs. And by DC analysis, what we mean is how do we bias the MOSFET to get the most out of it, to get the highest amount of gain out of it. So we talked about biasing an amplifier in the beginning of the course, but in terms of MOSFETs, we'll try to take a look at what biasing means. So that would be your homework number 4. That I have already posted, but it will be due on October 20th, so 2 weeks from now. Homework 5 is also posted, which will be October 27th, so 3 weeks from now, which will be on AC analysis of MOSFETs. And related to DC and AC analysis, whatever material that you need has already been posted. So please go through the intro to MOSFETs, MOSFET biasing, op-amps intro, as well as MOSFET amplifier analysis. So we'll go through all of these lecture material over the next week or 1.5 weeks so that we have ample time to solve the homework problems. There are similar problems related to homework 4 and homework 5, which have also been posted. So when you start solving them, please look into them, but there's still like 2 to 3 weeks of time for both of these homeworks. Okay. But all these homework problems, as well as the example problems that are there as part of these documents, which have been uploaded, that will help you to understand the DC and AC analysis of MOSFETs. And by DC analysis, we'll mean biasing. By AC analysis, we'll mean the analysis of gain for a MOSFET. Okay. So with that, let's go back to some of the basics. We are still not there yet where we can actually discuss about DC and AC analysis. We are just discussing the basics of MOSFETs. So let's get on with it. And over the next week or so, I hope we'll be in a position where we can discuss about DC and AC analysis for MOSFETs. Okay. All right. So last week, in the last lecture on Friday, we discussed about the physical structure of a MOSFET. Now, today we are going to talk about the IV characteristics, the current versus voltage characteristic for a MOSFET. And we'll take a look at it from two different perspectives. One from the energy band approach, and the other one from a mathematical model. We'll also try to build a mathematical model of the IV characteristic of the MOSFET. Okay. Now, when you think about the IV characteristic, as we talked about this earlier, that generally there is an input side and an output side for a MOSFET, right? So it's a 3-terminal device for all practical purposes. Of course, there's a 4th terminal called the body or the bulk terminal as well. But you have your control terminal, which is the gate. You have your source of majority carrier, which will be called the source terminal. And you have the drain or sink or collector of the majority carriers, which will be called the drain. So if you have a N-type MOSFET, which is this case, and how do you know that this is an N-type MOSFET? That is because the current flows out of the source and goes into the source, right? So if current goes into the source and majority carriers come out of the source, they are in the opposite direction of each other. And you already know that electron and current flow is in the opposite direction of each other. So in this case, what it means is that this is an N-type MOSFET or N-channel MOSFET, with the source being the source of majority carriers, which are electrons. And electrons are flowing from bottom to top, which means that the current is flowing from top to bottom. So in all MOSFET-based analysis, we'll always consider the source as the source of majority carriers and drain as the drain of majority carriers, be it an N-channel or a P-channel MOSFET. And the arrow over here will indicate the direction of current flow on the source, right? It will always be placed on the source, and it will determine the direction of the current flow. If it flows out of the source, it will always mean it's an N-channel MOSFET. If it flows into the source, it will always mean it's a P-channel MOSFET. Okay. All right. Now we'll talk about two different characteristics. One would be called the input characteristic. One is the output characteristic. Before going into the input characteristic, which will be very similar to a diode, let's take a look at the output characteristic of a MOSFET. And you've already got a glimpse of it in the last few lectures. But for the output characteristics, which is going to be your output current, the current flowing in the output terminal. So let's say this is the current that is flowing into the drain terminal. and this is the current that is flowing out of the source terminal. Okay. Now, as you already saw in the previous lecture, that at the gate there is an insulator by design and by structure, right? There is always going to be an insulator at the gate. That means there cannot be any current going into the gate. There cannot be any current flowing out of the gate. So that's not just possible at all for an ideal MOSFET. Of course, in a real scenario, there could be some amount of leakage through the insulator material, which is silicon dioxide. But in ideal scenarios, there would be no current flowing into or flowing out of the gate terminal. That means, according to KCL, the current coming into your drain terminal and current going out of your source terminal for this N-channel MOSFET is going to be equal. Because KCL states that the sum of the current coming into and going out of a terminal is going to be zero. That means if something is coming toward the drain terminal, the same amount of current has to come out of the source terminal. Okay. Now, any of those currents, the drain current or the source current, you can call that the output current of the MOSFET, because that's what you'll eventually be interested in. And that output current of the MOSFET, we already talked about this, that the MOSFET is a voltage controlled current source. So the output quantity is going to be the current. Now, the output voltage of the MOSFET is basically between the output terminal and the common terminal or the reference terminal. Because the source is grounded in this particular configuration, the source is going to be the reference terminal. Your input will be between your gate and your source. That's your input. And we'll discuss about all of this, that what does input even mean, right? It might not be very clear to you at this point that what does input mean, right? But when you discuss the examples, it will become clearer. But for now, let's just assume that, of course, you have three terminals. One of them is going to be the common between input and output. And as you know that the common terminal is going to be a ground, as you have seen in all electronic circuits. Your input terminal is going to be between, or input voltage is going to be between your gate terminal and that common source terminal. And your output is going to be in between your drain and source terminal. So this is where your output is going to be. And because source is the common terminal, you'll define your drain as the output terminal and your gate as the input terminal. And source is going to be the common terminal. And this particular configuration is called a common source configuration because, as the name suggests, the source is the common terminal. So this is called a common source configuration. We'll look into other configurations as well, that can you have a common gate configuration where your reference is the gate terminal and inputs and outputs are the other two terminals. We'll also look at a common drain configuration where your reference is the drain terminal and your input and output will be the other two terminals. So because there are three terminals, you can always do have the common terminal as any of those three terminals. This happens to be the scenario where your source terminal is the common terminal. Okay. But the other two scenarios are also possible. We'll discuss those possibly in the next lecture or either on the Wednesdays or Fridays lectures. Okay. But if you have your common source configuration, which is the easiest to understand, your input is at the gate, output is at the drain, and we'll discuss what input and output means in a moment. And your common terminal is going to be the source. Now, your output, as you know that the MOSFET produces an output current. So that output current is going to be your y-axis. And your x-axis is basically the output voltage in this case. Why? Because you want to look at the output characteristic, that how does the output current look like as a function of the output voltage. And we'll see that in this case, there would be three different regions of this output characteristic. One region would be called the linear region, where the output characteristic will look more like a resistor. That, okay, in this region, let's just only consider this region. Your voltage VDS is increasing, output voltage is increasing, so the voltage between your drain and source is increasing. And the current that you see between drain and source is also increasing. And it's a linear trend, just like a resistor. Any resistor, as you increase the voltage across it, the current will increase because of Ohm's law. So in this part, it behaves very much like a resistor, or we call this a linear region. And then there would be a region over here where you see that the current is saturating. And this is going to be called the saturation region because, again, the current is saturated. Now, the value of the current, the value of this current where it will saturate to, will depend on the voltage, gate voltage over here. So VGS, that's the gate voltage, gate to source voltage. But because your source is grounded, your VGS is basically your gate voltage, right? Because source is zero, source is grounded. the value of this output current is going to be dependent on the value of your VGS. If you apply more VGS, your current would look something like this. If you apply a lower VGS, your current may look something like this. Okay, so let's say VGS 0, VGS 1, and VGS 2, where your VGS 0 is the lowest gate to source voltage, VGS 1 is a little bit higher than that, VGS 2 is a little bit higher than that. So for 3 different values of VGS, where VGS 0 is lower than VGS 1 is lower than VGS 2. Okay. So in those conditions, if your VGS 2 is the highest, you'll get the highest amount of current at the output. And that's why this region is called the gate control current source. Why gate control current source? Because again, as you see that there's no control of your drain voltage does not determine the value of the current anymore. Now, of course, there is a small amount of slope here, but we'll see that that is a non-ideality. In an ideal scenario, there would be the slope will be absolutely equal to 0. So there would be no control of VDS over this output current in this saturation region. But the saturation region current will be determined by the gate to source voltage. So this is called the gate controlled current source region or the saturation region. All right. So in today's lecture, we're going to look at the formula for these three regions. And to understand that, first we'll take a look at an intuitive approach, looking at the energy band diagrams in a MOS structure. And then we are going to take a look at a mathematical approach as well. Now, if you have a silicon bar, so let's say, for example, you have this semiconductor or a silicon bar, and you know that for any material, electrons could be in valence band or in conduction band. So in valence band means that it is closely coupled to the nucleus of the atoms. And then you can have a conduction band where electrons are more free to move around. So let's say they are in the outer shell in the electron structure, and then they are more freer to move around. So there is a valence band and there is a conduction band. And this is just, these two lines are representing the energies in those two bands. Of course, in conduction band, the electron has more energy, and that's why it can move around. Whereas in valence band, it has less and less energy. And the lower energy you have as an electron, you will be more stable, right? So stability directly depends on how much energy does that electron have. So if you have a lower amount of energy, that electron is going to be more stable, and valence band electrons, which are again more stable, are lower than the conduction band location. Okay. Don't worry about all these other equations, because we are going to take an intuitive approach to understand this. All the equations are there in the slides, because if you take a device physics class, you'll know all these equations and you'll be able to derive all these equations. In this circuit class, it's not required to remember or understand all the equations that are written here in the next few slides, but this will just give you a reference and you can probably correlate that with any of your device physics knowledge. Here we are trying to take an intuitive approach of what will happen if we try to understand the MOSFET operation from an energy band diagram perspective. All right. So that's basically just for the semiconductor. Now for the metal oxide semiconductor, you basically have a silicon dioxide and then you have a metal gate. So this is your MOS structure. You have a metal, you have an oxide, and you have a semiconductor. Right? So that's how it looks like, just as a MOS structure, starting from the metal to the oxide to the semiconductor. Now, what would happen if you apply a voltage to the gate? So let's say we apply a voltage plus VG to the gate, a positive voltage to the gate. How would the voltage profile look like from the gate to the, let's say, end of the semiconductor structure? Because again, remember, this is metal, this is oxide, this is semiconductor, and this semiconductor is this long structure. And let's say you have connected ground to the end of this semiconductor structure. So let's say this is how the structure looks like, metal oxide semiconductor, and then you have connected your ground to the end of that semiconductor structure. So at the very beginning, on the leftmost side, you have metal and you have a plus VG voltage at that metal. The question that we are asking is that what would happen to the voltage profile along this semiconductor structure? So if you plot that, what is the voltage from the left side to the right side, you'll see that because you are applying a plus V voltage at the metal gate, you have some kind of oxide insulating layer. And then right below the insulating layer, you're basically creating this capacitor structure, right? You're basically creating this metal oxide semiconductor based capacitor. Now, metal is, of course, conductive, oxide is an insulator, semiconductor is somewhat conductive. So, let's say you're creating not a perfect capacitor, but somewhat of a capacitor. Now, you know that if you have plus Q charge on one plate of the capacitor, the other plate will hold minus Q, right? And that's how you analyze capacitor based structures. So, of course, you'll have a voltage develop at the metal side. So, you'll also develop a very similar amount of voltage if there is no loss between in the oxide layer. You'll develop a very similar amount of voltage on the semiconductor side as well. And because this semiconductor is not a perfect conductor, you'll not because and this side is connected to ground, let's say. And because the semiconductor is not a perfect conductor, if it had been a perfect conductor, then every point would have been connected to ground, right? Because if the conductivity of the semiconductor is infinite, then as soon as you connect ground to one part of it, everything gets connected to ground for the semiconductor, right? But because the semiconductor is not a perfect conductor, everything will not be connected to ground. So only this side, only the right-hand side where you are actually connecting the ground will have a voltage equal to 0. On the other hand, for the rest of the semiconductor structure, you'll see a gradual decrease in the voltage, starting from the metal gate, which was connected to a positive voltage VG, and then gradually you're going to that 0 voltage because it's a semiconductor. It's not a perfect conductor. It's not a perfect insulator. So you can think of it as a material which is having a high amount of resistance. So it's basically a large amount of resistance here, large resistance, and eventually, after all of those large resistances, you get this ground. So at every point, you'll have a voltage drop, and then gradually that voltage drop across all these resistors increase and increase until the point where you have the total amount of voltage drop equal to VG. And at that point, you reach 0 voltage anyway, right? So that's how the voltage profile will look like inside the semiconductor. And if you try to understand that from an energy band perspective, one particular assumption that we'll make, and again, this is not an assumption because you learned this in high school physics, that any positive potential will lower the energy of an electron. If you have an electron and if you subject it to a positive potential, what would happen is that that electron will have an energy of minus Q times V. So if the voltage is plus V, electron has a charge of minus Q, the energy of the electron is minus Q times plus V. Right? Again, just your high school physics. And if you have that energy equal to minus Q times V, if you increase your positive potential, let's say this plus V goes from 1 volt to 5 volt to 10 volts and so on. If this plus V is being increased, the energy is being reduced. Right? Energy will be minus Q times 1 volt, minus Q times 5 volt, and minus Q times 10 volts. So your energy is going lower and lower as you increase the positive voltage that you are subjecting your electron to. What that means is that the bands, the energy bands that we saw or tried to analyze in the previous case, that those energy bands will be bending because of the gate potential over here. So remember that you have a metal structure, then you have an oxide, and then you have the semiconductor. So you have metal, oxide, and semiconductor. And inside the semiconductor, you had the conduction band energy, you had the valence band energy. Of course, conduction band energy will be higher than the valence band energy. But this conduction and valence band energies will drop, or there will be some amount of bending toward the gate as you apply a positive voltage at the gate. That is just from the theory that if you subject an electron to a positive voltage, the energy of that electron will lower. And that basically bends this conduction band and valence band near the metal gate structure or just below that oxide layer. Okay. And this is the same thing as saying that your voltage, so what we saw in a few slides back, so let me go back. So you saw that the voltage profile looked like this, right? Now remember, if I now go forward, this is how the band profile looks like. And you know that the band energy, be it conduction band or valence band, that is minus Q times V. So if the bands are bending in this direction, right? Why are the bands bending in the downward direction? That's because as you're subjecting the electrons to a positive voltage, the bands will bend downward because the energy is reducing. Now, if the energy is reducing, at the same time, what it means is that if the energy is lowest at this point and then the energy is increasing toward this side, the voltage is highest at this point and then reducing on this side, right? So if I draw the voltage over here, now this was already your energy, but if I had drawn the voltage across that semiconductor structure, that voltage will be highest here and then it will drop towards the right hand side, because E is just minus Q times V. If your energy is more, voltage is less. If your voltage is more, energy is less. If your voltage is less, energy is more. Okay. And this is the same graph that we had drawn 2 slides back, that your voltage is highest just below that insulator, and then it goes to a zero potential when it is connected to the ground on the far right hand side of the semiconductor. All right. So this is why we are just writing the potential energy. So your potential energy is basically the energy in the conduction band minus Q times Vx. So your conduction band energy, which is the stable conduction band energy here and the stable valence band energy over here, you see some amount of reduction in those conduction band and valence band energies in this case. So as a function of the voltage within the semiconductor, you basically have ECB. So for example, your EC as an X, the conduction band energy as a function of X, where X is the distance along this X-axis. So that is going to be ECB minus Q times Vx, because you see that the energy is not fixed. It is reducing over here as a function of X. Question? So that's again your high school physics related concepts, that conduction band and valence band. What they mean is your electrons, if you know the atomic structure, that there is a nucleus, and around the nucleus, there are, let's say, these different circular paths or locations that your electrons can take. Right? Your valence band is basically all the electrons that are closely bonded with the nucleus, whereas your conduction band is, and you know how many number of electrons can be there in each of these cells, right? So for example, in this first circular path, you can have only 2 electrons. And then in the second one, you can have a maximum of 8 electrons. If you remember your periodic table from high school. So that's what it is based on, that how many electrons you have in your outer shell, that actually determines the column number that you have in your periodic table. If you have 1 electron, you have 1 that is in the first column in your periodic table. If you have 4 electrons, there will be 4, it will be in the 4th column in your periodic table. So silicon is in the 4th column. Silicon has 4 outer shell electrons because silicon is 14, right? 2 plus 8 plus 4. Those are the number of electrons you have in a silicon atom, right? Total of 14 electrons. Now, because you have 4 of those electrons in the outer shell, they can bond with other atoms. They can bond with other silicon atoms. They can bond with boron atoms, phosphorus atoms, and so on, whichever atom that you put in your structure. Right? And those conduction band outer shell electrons, they will of course have a higher amount of energy than the valence band electrons, which are closely bonded with the nucleus and which are stable. So for example, if you have 2 electrons over here, you are already filled up all the electrons that can be there in that shell. If you have 8 electrons in the next one, you have already filled up all the electrons that can be present in that shell. If you have 4 electrons in the outermost most shell, you haven't filled in all the electrons that can be present. And then they can create covalent bonds with another atom. So let's say there is another nucleus here, 2 electrons here, 8 electrons here, and then there is an outer shell. So it can create covalent bond between 1 electron in this atom and 1 electron in this atom. That's how. So you have 1 bond, and this is the second bond. Right? So again, remember your high school physics. I'm just talking about what you learned in your high school physics. Yes.
Like why? Like why do we need those? Like what is it like? What is the graph like really telling? No, I'm like trying to understand. like I get it, like it levels off, right?
Right.
But so what does that mean? Like, so I'm trouble understanding.
So what does this graph mean, or what does, for example, what? So this graph means what is the how does the bands, energy bands, look like in a MOS structure?
So it levels off. Like,
yes.
At a certain point.
Yes.
Okay. I was just
okay. All right. So that's how the bands look like, energy bands look like, and you already looked into the equation. So it's just a very simple first order equation that your ECB minus Q times Vx, where V is the voltage at any point along the x-axis. So this is your x-axis as a function of x. Your ECX and EVX changes. So ECX is the conduction band energy, EVX is the valence band energy, and without any application of a gate voltage, your conduction band would have been a fixed value here. Without any application of the gate voltage, your valence band would have been a fixed energy value here. Those are changing. That's what we want to show through this diagram. Now, if you take a derivative of this equation on the top, so you just have this equation, you take a derivative for that equation. And that derivative would be, of course, this is constant. So if you take a derivative, this will go away. The derivative of a constant is 0. Again, high school math. So you'll get minus Q times dV dx, right? You get minus Q times dV dx, and minus of dV dx is electric field. So you have Q times E, or Q times the electric field within the semiconductor structure if you just take a derivative of your energy bands. So graphically, this is how the energy band look like. If you take a derivative of this graph, how would that look like? It would look like this, right? Because again, when the previous graph, what does derivative mean? That when the graph is constant, the derivative of a constant will become 0. When the graph is, let's say, having a particular amount of slope, the derivative is the value of that slope. So this is how the electric field looks like within the semiconductor structure. For a metal oxide semiconductor scenario, when you are applying a positive voltage at the metal gate. Now, electron concentration, again, you don't need to remember any equations or anything, but again, intuitively, we are trying to make sense that how would these graphs look like, right? Because graphically is always more intuitive than trying to solve the math. So if you try to find out the electron concentration within the metal oxide semiconductor structure, again, you have a drop in the energy. So of course, that means that there are more number of electrons. So what is the energy? Like eventually, what is energy? What is the conduction band and valence band mean? It means the average amount of energy of the electrons in the conduction band or average amount of electrons in the valence band for this scenario, EVB. So if there is a drop in terms of let's say the conduction band energy or valence band energy, what does that mean? You cannot increase or decrease the charge of an electron, right? The charge of an electron is fixed. Can you increase or decrease that? No, right? You have already created a fixed amount of voltage. So you already knew that. Okay, let me go back a few slides. The energy of an electron, when you subject it to a voltage of V, is going to be minus Q times V, right? So you saw that your Q, or the charge of the electron, is fixed. The voltage that you're subjecting it to is again kind of fixed because you have a voltage applied at the gate and then you are not changing that gate voltage. You just have a fixed voltage. But we are still seeing that the energy of the electron, the average energy of all the electrons, those are changing. Your conduction band is bending, your valence band is bending. How is that happening? That can only happen if the number of electrons change. Because the energy of an electron is constant. But just because you have more and more number of electrons coming in just below the oxide layer, that's why the total amount of energy changes. It's the number of electron that is changing, not the energy of an individual electron. And again, just try to think about it intuitively, that you apply a positive voltage at the gate, which is further to the left-hand side. If you apply a positive voltage at the gate, you are going to attract electrons from this side. Whatever electrons are there on the far right-hand side, you are going to attract them because you are applying a positive voltage at the gate. That's all we are talking about. Again, everything is intuitive. Don't try to think about the equations. because equations are what you learn in a device physics class. Okay. So you're attracting all these electrons from the right-hand side, and that's why the number of electrons are changing. And number of electrons, since you have a higher number of electrons, you have a higher total amount of energy or average amount of energy for the conduction band or valence band on the left-hand side over here. Okay, that's all it means in terms of the graph. All right. Now, if you put it in the form of equation, again, I'm not going to emphasize too much on the equation, but you'll see that it will have an exponential relation with respect to the amount of voltage that you have at any point. So because the voltage we represented as Vx along the semiconductor structure, with this x-axis representing the distance x from this point, which is basically the junction between the oxide and the semiconductor structure. So it will have an exponential relation, and similarly, the hole will also have an exponential relation, number of, or the concentration of holes. So electron concentration will have a positive exponential. So of course, you'll have the highest amount of exponential or highest number of electrons toward the oxide structure, and then you'll have a low number of holes near the oxide structure. So the hole concentration reduces near the oxide structure. Again, remember that you have a metal gate, you have an oxide structure, and what we are plotting here is whatever happens inside the semiconductor. So x equal to 0 is just the interface between the oxide and the semiconductor, and x equal to the highest value that represents the point where you are grounding the semiconductor structure. So the number of holes, they are reducing towards that oxide semiconductor interface. Why is that? Because you have applied a positive voltage at the metal gate. So the number of holes or free holes that are present in the semiconductor structure, those are reducing. Okay. On the other hand, electrons will be increasing. So the red signifies how the electron concentration looks like, and the dark blue signifies how the hole concentration looks like. Now, this is the region. Why do you call it the depletion region? Why do we call it the depletion region? Because think about it that, let me go back one slide. The hole concentration was high in the semiconductor structure because we start with a p-type semiconductor. This is an n-channel MOSFET because you're applying a positive voltage at the gate. So if you want to create an n-channel MOSFET, you start with a p-type semiconductor. And in a p-type semiconductor, you have excess number of holes. So you start with a very high number of holes and a very low number of electrons, because electrons will be minority carriers, whereas holes are majority carriers. What you're doing here is that you're exponentially increasing the number of electrons and exponentially reducing the number of holes. But still, because you started with a very low number of electrons and a very high number of holes, if you plot this in linear axis, so this is what is plotted in a log axis, but if you plot it in a linear axis, this is how it will look like. That your hole concentration will suddenly drop and start dropping exponentially. Your electron concentration was very low to start with. It will exponentially increase, but it will still remain very, very low as compared to the hole concentration. And this region is going to be called the depletion region because here you neither have holes nor electrons now. And that's what is meant by depletion region in the first place, that you deplete it off with respect to any kind of charge carriers. All right, so what we discuss is how do we read the band diagrams. So basically your energy band, and energy of an electron, as you know, is minus Q times V. So the voltage will be proportional to minus of the energy band diagram's value, or the energy band diagram. The electric field is going to be the derivative of that energy band, and number of electrons and number of holes that you can also calculate as an exponential relation with respect to that energies in the energy band. Now we are trying to, because that's what we saw for a MOS structure, a metal oxide semiconductor structure. Let's take a look at how the energy bands look like in a PN junction diode. And then we'll try to combine both of them. How does it look like for a MOS structure and how does it look like for a PN junction? And then we'll try to figure out how does it look like for a MOSFET. So when you're trying to draw the equilibrium energy band diagrams for a PN junction diode, let's say you have the N side on the left side. So this is your N and this is your P. Again, red signifies more electrons, dark blue signifies more number of holes. So electron concentration high on the left side, hole concentration high on the right side, and electron concentration will be low on the right side. And in between, you'll have the depletion region, basically. Now, if you try to draw the energy band diagram in this case, first what you start with is drawing a reference line. And as you'll see later, and if you have taken any device physics classes, you'll know that reference line will be called the Fermi energy level. So EF, E subscript F, that represents the Fermi energy level. And EC, the conduction band energy, is going to be low, where the electron concentration is high. Again, why? Because if you have more number of electrons, right, each electron will have a minus QV times energy. If you have more electrons, your total energy will be low because it's minus QV. So it's in an absolute term, it will have a higher value, but because it is minus QV, the negative number will be a lower number. And EC is going to be high where the electron concentration is low. So if the electron concentration is low, energy is higher. If the electron concentration is high, energy is lower. Again, just from that assumption that we made from your high school physics. All right. Now, if we assume that to be true, then this is how the conduction band energy will look like for an NP junction. So the N was drawn on the left side. The energy will be low when the electron concentration is high, and energy will be high when the electron concentration is low. Okay. Now, you know that the conduction band and valence band, they will always have a fixed amount of difference between the two. Then that is true for silicon, for the material. The material will have a particular amount of work function, and it will have a particular amount of energy for an electron to go from the valence band to the conduction band, or vice versa. That's a material property, that how much electron you need for an electron to move between valence band and conduction bands. So if the electron is in valence band, you need to add some amount of energy for the electron to go to the conduction band. And if the electron comes back from the conduction band to the valence band, it releases some amount of energy. Right? Again, high school physics and chemistry on atomic structures. So how does this electron energy band diagram, or why does the energy band diagram look like this in this case? So remember, we started from this straight line, which we call the Fermi level energy. What does this signify? The Fermi energy signifies the average amount of energy for an electron for the entire structure. So it's an average energy that an electron have in the entire structure. Why is this important? Because this tells us, be it a p-type semiconductor or an n-type semiconductor or a p-n junction diode or a MOSFET, there would always be an average. If you take all the energies of the electrons, you'll just get an average number. And the Fermi energy gives you that average number. Now, the average energy value in the n-type semiconductor, as you see over here, is closer to the conduction band. And the average energy value toward the p-type is closer to the valence band. Why is that? Again, that's because you have more number of free electrons on the inside. So if you have more number of free electrons, you're closer to the conduction band, because those free electrons can move around. And what does conduction band mean? That the majority charge carriers can do charge conduction or current conduction. So it's very easy to do charge conduction if your average energy is very close to the conduction band itself. On the other hand, on the right-hand side, the number of electrons are very small, and they are very close to, or the average energy is closer to the valence band. It's not very easy for the electrons in the p side to carry current. So that's what this curve signifies. And of course, at the same time, because if you have higher electron concentration, your amount of energy in the conduction band or valence band will be lower. That's what you see on the left side of this graph. And the conduction band or valence band energy is higher on the right-hand side of this graph. Now, as you have learned in the previous slides, that if you want to plot the voltage, right? If you want to plot the voltage along this PN junction structure, you already know that the energy is, if you plot EC, or the conduction band energy, as a function of x, where x is your x-axis. So that's going to be some fixed value. You can consider, let's say, this highest value as ECB minus Q times Vx. That's going to be your EC as a function of x. So if you plot the voltage is going to look something like this. It's exactly opposite to the previous diagram, because voltage and energy, they are related with each other with this minus term. That if your voltage is higher, energy will be lower. If your voltage is lower, energy will be higher. So the voltage across a PN junction will look something like this. Now, again, if you start from the conduction band diagram, and if you take a derivative of it, you know that the derivative will give you the electric field across the PN junction structure. So if you take a derivative of this, the derivative looks like this. Why? Because again, on the left side, let's go back to the previous slide. On the left side, you have a constant energy. On the right side, again, you have a constant energy. The derivative of any constant value is going to be 0. And only when you have a slope, your derivative will be non-zero. So near the PN junction, you'll have a non-zero electric field. Everywhere you'll have a zero electric field. And we didn't talk about this much, but this is something that in device physics it's impressed upon a lot, is that you do not have an electric field toward the beginning or the end of the PN junction structure, but only near the actual junction where you are switching from a P-type semiconductor to an N-type semiconductor. Near that actual junction, you'll have electric field. And according to the electric field, you'll have a built-in potential. That there would always be a built-in potential, inbuilt potential around that junction, which is very important in some of your device physics classes. We'll kind of not go into the details of that built-in potential in this particular class, but this is the reason. Like if you kind of try to look back to your device physics classes and try to correlate with that, you'll understand this, that because your electric field, which is the derivative of that energy band diagram, that has a non-zero value around the junction and zero value around the two ends, it's near the junction where you create that built-in electric field and built-in potential. And again, electron and hole concentration, you can probably plot from here, and they will look like this. That your electron concentration will be higher on the N side. Your hole concentration will be higher on the P side. So this is the P side of the junction. This is the N side of the junction. Electron concentration is high over here, and then that will gradually drop on this side. The hole concentration is higher on the P side, and they'll drop over here. In the middle, both N concentration and P concentration are reducing, and that's why you'll have the depletion region. All right, so why did we learn all of this? So the energy band diagram is basically a powerful tool in understanding the operation of a semiconductor device. It gives you an idea about how does the electric fields look like, how does the voltages look like, how does the electron and hole concentrations look like within a semiconductor structure. Again, this is not something which is very important if you want to be a circuit design engineer, because nobody will ask you that question in a circuit interview. But it's important to understand how the circuit operates, and how the circuit operates depends on the physics of the device. So I just wanted to spend some time on the physics of the device and how that energy band diagram and everything related to that looks like. All right, so let me skip through this. Now, if you do an energy band treatment for the MOSFET, so right now, till now, what we looked at is energy band treatment for a MOS structure, metal oxide semiconductor, without the source and drain regions. We never looked into the source and drain regions, right? And we looked into PN junction diode. So if you have N over here, you have P, you have N. So we looked into what happens near a PN junction for a PN junction diode. We looked into what happens for a PN junction diode over here. And we looked into what happens for a MOS structure. So if you have a metal oxide semiconductor. So we looked at this direction and we looked into this direction, but we never looked into both of them at the same time. right? We just looked into what happens for a p-n junction diode and what happens for a MOS structure in terms of the energy bands. All right. Now, in this case, to understand what would happen for a MOS structure, we'll consider our x-axis along the channel. So through the source, through the drain, and then so source, then channel, and then through the drain. So we'll look into the energy band diagram in this case. And remember that this is N, this is P, and this is N once again. So how does it look like? Sorry. So because this is NPN, and you already know that for a N-channel semiconductor, the energies will be lower. For a P-channel semiconductor, the energies will be higher. And again, for the N-channel or N-type semiconductor, the energy will be lower. Why is that? Because N-type semiconductor, more number of electrons means less amount of energy. Same thing that we discussed throughout the class. So you have your N-type semiconductor on the left side. That's basically your source. You have your P-type channel in the middle. And then you have your N-type drain on the right-hand side. So basically you have source, channel, and drain. And this is how the energy band look like in the source, in the channel, and in the drain, because you're just combining two p-n junction diode now. So you already saw this half in the last few slides. You just mirrored that half and connect it on this side. So you basically get the entire NPN, what is happening between the source, the channel, and the drain. All right. So basically it's the same structure. We are not going to look at the valence band anymore, because you know that the conduction band and the valence band will always have a fixed amount of energy gap between the two. So if you just look at one of them, it's sufficient to understand what is happening to both conduction band and valence band. So you have source, channel, and drain. And your electrons are on the source side, because source is the majority carrier, source of the majority carriers, which are the electrons in this case, because you are looking into an N-channel source, then a P-channel, N-type source, then a P-type channel, and then N-type drain. So your majority carriers are the electrons. And electrons want to go to this side, but electrons do see a wall in between. So this is basically you want to, let's say, jump to the other side of the wall, but either you need to jump up or you need to have sufficient amount of energy to kind of break through the wall to the other side. So that's what this energy band diagram signifies. And now we can probably relate it to what we are going to say in the next few slides. So this is without any, let's say, voltage applied at the gate. Now, if we apply a voltage at the gate, what would happen? If we apply a voltage at the gate, this barrier or the voltage or the potential or the energy that you had at the channel, that will reduce. So earlier, initially you had this tall wall. But as you apply a positive gate voltage, over here, the height of that wall reduces. Why? Again, the same concept. The energy of the electron reduces as you apply a positive voltage to it. So you apply a positive gate voltage, the energy of the electron reduces, and you get a lower height of the wall. So now you can easily understand that for an electron which is over here, it becomes very easy for that electron to go to the drain side if the height of the wall is reduced. You don't have to jump up high. You just have to cross a very small barrier between the source and the drain regions. And that's why by applying a positive gate voltage for a N-channel MOSFET, you are making sure that the flow of the electron from the source side to the drain side becomes easier, because the height of the wall reduces as you apply that positive gate voltage. So these electrons, now one thing is that you have applied a positive gate voltage and then you have reduced the height of this wall, but still you do not have a voltage difference between the source side and drain side, let's say. Or let's say my source is negative and my drain is positive. So you still do not have a voltage difference between the two. But if I apply a voltage difference between the two, what would happen in that case? Till now, VDS is 0, let's say. And because VDS is 0, there's no flow of electrons. Now, if you make gate to source voltage higher than, let's say, some kind of a threshold, and at the same time, if you create a VDS which is greater than 0. So this is the drain side, and this is the source side, and this is what you have at the gate. So on the drain side, you apply a positive voltage, and you apply a negative voltage at the source. So your VDS is positive. If your VDS is positive, what would happen to the energy band? The energy band will reduce even more on the drain side, because the drain side has a positive voltage. The source side is, let's say, grounded. The drain side has a positive voltage, so this energy band reduces even more on the drain side, and that creates a slope on this energy band. So now imagine this as that's a mountain with a slope. Now if you have this electron, which is a ball, and if you just roll that ball on top of this mountain with a little bit of energy, because you don't need a lot of energy as the height of the mountain has reduced, what would happen to the ball? The ball will just roll down to the right-hand side. And that's what happens in a MOSFET. Let's stop here. We'll continue from this in the next lecture.